Welcome to Massive Open Online course on fluid flow operations. Today in this lecture, we will discuss about one dimensional flow as part 2. In part 1, we have discussed regarding the continuity equation and its application with different examples, and based on that we have discussed how the fluid will be behaving whenever it will be flowing through a pipe. Now, as per basic equations of the fluid flow, we have discussed that conservation of mass flow. Under that, what should be the continuity equation? Basically, this conservation of mass flow is called the continuity equation, whereas other principles like principle of conservation of energy, which is called the energy equations, and the principle of conservation of momentum is called momentum equation. So, and other auxiliary equations, we can say that to consider along with these basic equations of the fluid flow, that are law of thermodynamic properties, equation of state of perfect gas, and law of thermodynamic properties are generally analyze compressible fluid flow, and equation of state of perfect gas will be considered for behavior of physical properties of the gas. So, we have already discussed about the principle of conservation of mass flow, and in this lecture we will go through some equations which are related to that energy, and also how it is derived, and also some examples of on that energy equation. Now, if we consider that conservation of fluid energy, here see the pictures, here see how whenever fluid is just releasing from a tank through a pipe, and there if a pipe is not horizontal, and if it is suppose there will be a what is that certain bend of this pipe, and also the cross section of the pipe will be changing, and based on which how energy is consuming, and during that consumption of the energy, you will see total energy will remain same, because we cannot create any energy for that. So, total energy will remain same, but only thing is that energy will be transferring from one form to another form. Like here 3 energy, if we consider here, one is potential energy, another is kinetic energy, and another is called pressure energy. So, there are 3 types of energy. If I sum this, you will see in that at any location of this pipe here shown that the total energy will be same. So, here at a particular location, let it be here at this position. So, here what should be the pressure energy here, that pressure energy, and what should be the kinetic energy based on the fluid velocity, and what will be the potential energy based on the height of the fluid at which it will be flowing. So, total energy of these 3 forms will be equals to same in all cases. So, you see here another point here, let it be potential energy 30 kilojoule, and kinetic energy will be 0 here, because there is no velocity at this point. Here there will be a certain potential energy. So, summation of energy will be same in all locations here. Similarly, in other locations, suppose if we change the velocity at these locations, the first figure that here the velocity at the outlet of this fluid from the pipe will be higher, and there you will see that kinetic energy will be higher, because it is coming from the pipe at a certain velocity, and this potential energy will be maximum there, and kinetic energy at this whenever it will be releasing and it will going downward at this maximum point, there will be no velocity. So, kinetic energy will be equals to 0. Whereas, here potential energy will be pressure energy will be certain extent, and then potential energy will be the maximum. Whereas, in the bottommost figure here, you will see there will be some nozzle will be used at the outlet of this pipe, and cross sectional area will be very small. In that case, velocity will be very high, because the liquid is coming through that nozzle and liquid will be coming as a liquid Z. But that position there will be a higher velocity, so higher kinetic energy relative to the potential energy and pressure energy there. So, in this case we are just saying that the conservation of the fluid energy will be satisfied if summation of the energy will be remain same and it will be constant there. So, sum of different forms of energy is constant. This is the principles of conservation of fluid energy. Based on this principle of energy, we will derive that Bernoulli's equation. This is one of the important energy equations to apply the fluid flow phenomena, to apply the fluid flow in a conduit or any other applications in real life. They are so Bernoulli's equations, and this is applicable whenever fluid will be flowing at a uniform condition. So, in this figure, if you see that the picture here, in this case, if we consider that one control volume of this fluid element and the fluid is flowing at a velocity v, and streamline of this fluid element will be the same in the direction of the fluid velocity, and it is chosen with the coordinates shown in figure here like this. Here this is in the v direction, that is here v, and it will be certain angle with the horizontal. So, there will be pipe flow, there will be a flow in through the pipe is inclined at an angle theta, and through which there the liquid will be flowing. So, in that condition, if this cross section of at this point of this pipe is dA, and at this point there will be a, suppose here again the same cross sectional area dA. So, and the length of this fluid element is considered as ds, and if we are considering that this is your streamline, and then these are the streamline and the uniform velocity is there. So, this uniform velocity is v. So, what should be then force acting on this element, and after that how energy can be calculated based on this force. Now, what should be the net force applying in this fluid element. So, how to calculate there. So, whenever fluid is flowing, that at this cross section there will be some pressure. So, there will be some pressure energy, pressure will be exerting on this cross section, and at this cross section in the opposite direction this pressure will be there. Now, this pressure at this outlet section will be some increment of the pressure along with this distance of this pipe or length of this fluid element there. So, in this case what should be the pressure at this section? Pressure at this sections I have to calculate. So, in the inlet section pressure will be P into dA, and at the outlet section the pressure will be P plus dou P dou S into ds as shown in your figure also. This is in the direction of the streamline. Similarly, at a time there will be a force acting due to the gravitation. So, the gravitational force will be m into z. So, here mg is what? That mg means rho into volume, that is rho into dA into ds into z. So, it will be your gravitational force, but gravitational force will be acting that is in the downward directions, but here if we consider the direction of the streamline flow, then we can say that gravitational force in the streamline, that is opposite to that streamline flow, will be equal to rho dA ds into z cos theta there. So, if we consider that what should be the net force, then what should be the in the v direction streamline direction, at the direction of the streamline, then what will be the force acting, and what will be the force acting that opposite to that streamline direction. So, opposite to that streamline only gravitational force is acting. So, if you look at this equation number 1, we can get P into dA first term. So, P into dA is nothing but the force applying to this cross section dA, and P plus dou P dou S into ds, this is the pressure. This is the pressure which is acting at the section 2 in the opposite direction of this flow. and if we multiply it by dA, then it will be force. So, P plus dou P dou S, dou P dou S is nothing but what is that pressure increment or more pressure according to that length ds, and if you multiply this ds, so dou P dou S into ds, this will be your pressure increment, and then P plus dou dP into dA, this will be your pressure, total pressure that is acting opposite to this flow of direction. And then minus gravitational force in this the component of the gravitational force in this streamline, that will be rho into dA ds into z cos theta. So, that will be finally minus dou P dou S ds into dA minus rho into dA ds into g cos theta. What is rho? Rho is the density of the fluid, and dA is the small element of the cross sections here, theta is the angle at which this pipe is inclined to this horizontal, or flow is flowing at an angle theta to the horizontal. And then what is that? This is your F net. Now, if we apply the Newton's law, then F net will be equal to mass into acceleration, that will be equal to rho dA ds into dV dt. So, dV by dt is nothing but the acceleration of the fluid element. So, in this mass into acceleration, that will be your F net. So, rho into dA into ds, this is your mass, and dV by dt is nothing but the acceleration. So, this if we equate this equation number 1 and equation number 2, then we can have this equation number 3 as dV dt, that will be equal to minus 1 by rho dou P dou S minus g cos theta. This is after simplification. Now, we can say that from this equation, this acceleration will be is equal to that means density average of pressure gradient, and minus this what is that gravitational acceleration opposite to that direction of this flow stream, and it will be represented that as gravitational acceleration component at g cos theta. And the velocity may change with the both position and the time. So, in that case in a non dimensional flow it therefore becomes a function of distance and the time also. So, if we consider that if your dV is equal to dou V dou t into dt plus dou V dou S ds, then this will be your what is that velocity increment with respect to distance and time. So, the acceleration will then be calculated from this equation number 4 by dividing dt, then it will be dV by dt, that will be equals to dou V dou t into dt, dt will be cancelled out, and plus dou V dou S into ds by dt, that will be equal to simply dou V dou t plus here ds by dt. This is the fluid element distance, it will be by divided by d, this is nothing but distance by dt, that is the velocity. So, it will be V and dou V by dou S. So, dou V dou t plus dou V dou S, it will be your acceleration term. Now, if we equate this equation number 3 and 5, we can we can simply will be able to calculate what will be the velocity distribution. Now, before going to that, we have to actually calculate what should be the value for dou V dou S here. Now, dou V dou S to calculate here, interesting that to get this dou V by dou S equation, for that from the geometry we can calculate here what should be the cos theta in terms of ds and dz. So, cos theta will be equal to dz by ds as per what is that geometry here. So, it will be here this mass is your what is that what is that this mass is your ds, and this mass is your ds, and this is your dz. So, ds into cos theta, this will be your dz. So, we can write dz by ds in equation number 6 as cos theta. So, equation number 3 becomes with equation number 5 dou V dou t plus V dou V dou S, that will be equal to minus rho 1 by rho dou P dou S minus g into dz ds. So, this is your simplified equation. Now, see dou v dou t will be equals to 0 for steady state condition, and this part minus 1 by rho into dou p dou s, this part will be equal to pressure gradient and per unit volume, and also here this g into dz ds, this will be a gravitational component. Now, total equation can be simplified as v dou s is equal to minus 1 by rho dp by ds minus g into dz by ds, because the steady state condition dou v by dou t will be equals to 0. Now, this form of equation 8, it is called Euler's equation, and Euler's is an eminent mathematician born in Switzerland, and he has given or he has derived this equation earlier. So, as per his name, it is represented as Euler's equation. Now, in this case you have to remember that in incompressible fluid flow with two unknowns, suppose V and P, the continuity equation you have to solve simultaneously, and for compressible flow this pressure becomes unknown too. In that case, by adding a third equation of state for a perfect gas, a solution can be obtained, because here density will be changing with respect to pressure also. Again, if we go to that equation number 8, and after integration of this equation number 8 with respect to that distance of that fluid element, to obtain a relationship between points a finite distance apart along with the streamlines, as here v square by 2 plus integration of dp by rho plus gz, that will be equal to constant. So, this is your equation number 8. Now, you have to integrate this. So, after integration we can get it here, this is simply v square by 2, and here this will be integration of dp by rho, and here it will be coming as what is that, g into dz, and that will be equals to constant of integration. So, finally, these three terms, summation of these three terms will be equals to constant. Now, and for an incompressible fluid where rho will be equals to unchanged, that means constant. So, in that case v square by 2 plus this p by rho. So, in this integration here there will be no change of this what is that, density. So, we can segregate this one by rho, and then p dp integration it will be only p. So, p by rho plus g z, that will be equal to constant here. What should be the unit for this v square by 2? It is nothing but meter square per second square or joule per kg. That means, here what will be the energy per kg, that is represented by this equation number 10. Now, if we multiply each term by rho, then we can get here rho v square plus here p plus rho g z, that will be equal to constant. So, what will happen here, rho v square by 2, this is what is called kinetic energy. This is as you can say as pressure, and this is also P. What is the unit for rho v square by 2? This is the unit for pressure. So, it is Newton per meter square, and rho g z is the what is that potential energy. This is also that as a pressure rho g z, this is Newton per meter square. So, here, so equation number 10 we can represent it by equation number 11 also, and here in this case, if we again divide this equation number 10 by g, that is gravitational acceleration, then we can have here b square by 2 g plus p by rho g plus z, that will be equals to constant. Now, v square by 2 g is nothing but the velocity head. This is in terms of head y. This is the unit of that means distance here, that is m. So, v square by 2 g is nothing but H here, H is the head, H is called head. So, v square by 2 g it is called velocity head, P by rho g this is the pressure head and Z is the potential head. The unit for these each terms is m meter only. So, that is why you can say this is the head. So, velocity head, pressure head and the potential head, and the summation of these three heads are called total head. Now, this total head will be equals to constant. So, this is your Bernoulli's equation, one form of Bernoulli's equation there. And so, these Bernoulli's equations are applied only for uniform flow in this case. Other limitations also are there, we will discuss later. And so, this is the conservation of energy. You can say that total energy will remain constant there. So, v square by 2 g this is velocity head plus p plus rho g plus z, that will be equal to total head will be constant, and in terms of energy you can say v square by 2 plus p by rho plus g z, that will be equals to constant in equation number 10. So, this is called the conservation of energy. And if we consider that the flow is not uniform, so in that case what will happen? So, in a real fluid you will see that there is a cross section in which through which the flow will be there, and in that case the velocity distribution will not be uniform, because the cross sectional area will change. So, in that case maybe for lower cross sections the velocity will be higher, and for higher cross section velocity will be lower. So, in that case you will see the flow of the fluid will not be uniform in nature. So, in that case the kinetic energy per unit weight of the fluid that will be transferred across the section will be greater than that of calculated by using average velocity. So, if we consider only average velocity, there will be some kinetic energy per unit weight, but if we consider that in cross sections without taking average velocity, actual velocity, then the kinetic energy will be of course greater than the than that calculated by considering the average velocity. So, hence kinetic energy per unit weight in this case can be expressed as kinetic energy true, that will be the alpha into v square by 2 g. That means, you have to multiply some factor with the that means kinetic energy, that is v square by 2 g. So, this alpha is the multiplication factor, and this factor is called the kinetic energy correction factor. This kinetic energy correction factor will be 1.03 to 1.06 for the turbulent flow. If there is a turbulent flow, in that case you will see there will be non-uniformity of the fluid flow. And for laminar flow generally this laminar flow almost uniform in flow. So, in that case the alpha should be equal to 2, finally, then v square by g will be your kinetic energy there. So, in that case you have to remember that the kinetic energy correction factor for turbulent flow will be equals to 1.03 to 1.06, whereas for laminar flow it will be 2. Now, finally, with this correction factor the Bernoulli's equation can be expressed as alpha into v 1 square by 2 g plus p 1 by rho g plus z 1, that will be equal to alpha into v 2 square by 2 g plus p 2 by rho g plus z 2. What is this 1 2? 1 is the cross section 1 and 2 is another cross section there. So, through which this flow will be flowing. So, in the cross section 1, in that case what will be the kinetic energy and what will be the potential energy and the pressure energy. Summation of these three at these sections will be equals to summation of these three energy, that means here kinetic energy, pressure energy and potential energy. At these two sections the summation of this energy at these two sections will remain same there. So, that is why you are equating at these two sections the summation of this energies there. What will be the limitations of these Bernoulli's equations? So, generally these Bernoulli's equations are applied when velocity is uniform over the cross sections, and where fluid is non-viscous also, in that case frictional losses will be 0. So, Bernoulli's equations are applied only for those conditions, and also their flow should be steady, and for unsteady flow Bernoulli's equations are not applied, and flow is done along the that means streamline. So, whenever you are considering the energy, so you have to consider the flow will be along the streamline. What should be the flow if it is suppose not in a streamline, it is vertical or some other forms, then you cannot apply this Bernoulli's equation. And in the case of fluid where homogeneous and incompressible conditions will be there, then only you can apply the Bernoulli's equations. And also except gravity and pressure force, no other forces or energy is involved in this Bernoulli's equation. So, these are the limitations of the Bernoulli's equation that you have to remember. Whenever you are going to apply these Bernoulli's equations, that you have to keep in mind those I think limitations there. Now, based on this Bernoulli's equations, we can have what should be the dynamic pressure, static pressure and stagnation pressure. So, if the streamline is horizontal, suppose flow is flowing, if it is horizontal in flow, then you can say the term rho z h will be neglected, because they are both the sections the height will be same. So, in that case potential energy differences will be 0. And in that case if we consider that Bernoulli's equations there, so it will be rho v square by 2 plus p plus here potential energy is equal to 0, and that will be equal to total pressure here. So, rho v square by 2, this is also pressure energy and this is your pressure energy. So, this one is called rho v square by 2, it is called dynamic pressure, and P s that is called static pressure, and this total of this dynamic pressure and static pressure, it is called total pressure, or sometimes it is called stagnation pressure. So, if the horizontal pipe fluid is flowing, so in that case we are getting two types of pressure, dynamic pressure and static pressure, and summation of these two pressures is called the stagnation pressure. Now, again the Bernoulli's equation, that means energy, conservation of energy will be satisfied here. So, if we consider two sections of this pipe here, cross section 1 and cross section 2, then you can say this summation of this dynamic pressure and the static pressure will remain same. So, in that case here you can say in terms of head V 1 square by 2 z plus P 1 by rho z, that will be equal to V 2 square by 2 z plus P 2 by rho z, that will be equal to total head. So, total head based on this what is the dynamic pressure and static pressure, that will be remain same. So, if I consider here this figure, what happened, you will see these two cross sections here, cross section A 1 and cross section A 2. So, in this case the velocity of this fluid will be V 1 and velocity at this sections will be V 2. And then what will be the energy here in this case V 1 by 2 z, V 1 by 2 z is the what is that, it is called kinetic energy, and this is your P 1 by rho z, it is called pressure energy. So, total energy will be equal to what is that, this is total energy, and it can be represented by the head also. So, P 1 by rho z is called pressure head, and V 1 square by 2 z it is called velocity head, or yeah, simply you can say it is already velocity head we have told. So, these two heads, that is velocity head and the pressure head, summation of this it will be equal to total head. And here again if you consider this cross section 2 here, what should be the pressure head up to this, and this one will be your velocity head. So, summation of these two head will be equals to total head. So, this is your principle of energy. So, we can say that total head in this case will remain constant. So, very interesting that whenever if you are getting the cross section is greater than another cross section, one cross section is greater, suppose here A 1 is greater than A 2. In this case of course, then we can say that V 2 will be is greater than V 1, V 2, if A 1 is greater than A 2, then you can say V 2 will be is greater than V 1, because here cross section is in the section A 2 will be lower. So, higher velocity will be there. whereas cross section is higher in this section A 1. So, velocity will be lower. So, in that case V 1 is less than V 2 and you can expect that P 1 will be greater than P 2 there. So, where the flow channel is narrow, you can expect that the streamlines will be more dense and the flow velocity will be large and the pressure head will be low there. So, in this case very interesting that since the total head will be constant. So, if velocity head increasing, then pressure head will be decreasing. Similarly, if pressure head is increasing, then velocity will be decreasing. So, this is the principle. So, based on these Bernoulli's equations and the conservation of energy, we can calculate what should be the dynamic and static pressure, and also the summation of these two will be represented as the stagnation pressure. Now, another important aspect of this fluid flow phenomena based on this energy principle, it is called hydraulic grade line and the energy line there. So, we know that the total energy will remain constant there as per principle of the energy. So, in that case, suppose allow to flow the water from one reservoir to another reservoir at a certain elevation level to another level. So, we can say that there will be a flow of liquid, and also whenever it will be flowing through the pipe, we are just changing the cross section of the pipe somewhere else. So, in that case, if we consider that in these sections where the section height is Z 1 and this is the section where the section height is Z 2 and this section where section height is Z 3. So, we can say that here in the section 1, what should be the energy, that means here potential energy or head, as per head we can say that potential head is Z 1 and the pressure head is P 1 by rho z, and here the velocity head will be V 1 square by 2 z. Total 3 heads, if we sum it up, then it will be total head. So, again here if we consider at these sections the here potential head, pressure head and velocity head, we will see that summation of these 3 heads will be equals to total head, but here we are not getting here. If we consider this line red line, this red line is called the energy line. So, it should be constant, but sometimes in real flow we are not getting through this line, we are not getting the total head constant. Why? Because there will be some energy loss during that operation. So, that loss should be considered. If we consider that loss head loss it is called. So, that will be considered, then total head will be remain constant. So, here at these sections there will be a certain I think loss of head, because whenever fluid is flowing from this cross section to this another cross sections, there will be a certain change of kinetic energy, and also there will be some loss of energy there. And based on that loss, if we consider that it will be H 2, then the total head will be H 2 plus here what is that velocity head V 2 square by 2 z plus pressure head plus potential head. So, here 4 components 1, 2, 3, 4. So, the 4 components of head that will give you the total head. Here at this sections also, here certainly this higher cross sectional area to the lower cross sectional area, here also there will be a certain change of energy, that means some loss of energy will be there. So, in that case potential energy will be here at a certain height, it will be Z 3 and it will be your pressure head, and there will be some kinetic energy head and there will be a loss H 3 there. So, in that case the real fluid case real flow, you have to consider that there will be a certain loss of energy. So, that loss of energy to be considered there to get the conserved of the energy equation. So, if there is no head loss, then simply this summation of this velocity head, pressure head and potential head will be total head, and if there is a certain head loss, then you have to consider there. Now, you will see whenever you will supply any energy from one location to another location, there will be some useness of some machines to just deliver this fluid one location to another location. In that case, that machine will supply some energy to the fluid, and in that case you have to consider what should be the what is that head due to that supply of that external machine or by devices to discharge this liquid from one location to the another location. So, they are very interesting that for that there will be some head, that head should be also be considered there in your energy equation. So, as per Bernoulli's equations or energy conservation of energy. So, V 1 square by 2 z plus P 1 by rho z plus Z 1 plus A c. A c is nothing but the here head due to the supply of energy to the fluid by external device such as pump between the two sections there. So, that will be considered here, and then it will be equal to V 2 square plus 2 z plus P 2 by rho z, that is pressure head, and Z 2 that is potential head plus H 2 is the head loss here. And again at section 3 the summation of this velocity head, pressure head, potential head and the head loss at this sections 3. So, you will see that the total energy will be remain same, that will be equal to total head. So, we can say from this concept, energy concept, we can generate that what will be the hydraulic grade and energy line. Now, this hydraulic grade is nothing but the you have to sum it up of only two components. One is the potential energy and the pressure energy, that means potential head and the pressure head. Summation of these two heads are will give you that what is that hydraulic grade. And here at this location also what should be the what is that pressure head and the potential head, pressure head and the potential head, that will give you that hydraulic grade line. Whenever you are adding that dynamic pressure, that means here velocity head, then and the energy loss or head loss, that will give you the total energy. So, energy line without considering the head loss, then what should be the line there? This will be your the red line is represented by this energy line, whereas the dotted green line is represented by the hydraulic grade line here. So, from this figure you will be I think able to understand what should be the actually how this grade line and energy line, hydraulic grade line and energy line can be generated based on this energy component. And let us do an example for this Bernoulli's equations, and in this case suppose a liquid is flowing in a horizontal pipe at a flow rate of 0.05 meter cube per second. The length of the pipe is 200 meter and its center is 3 meter above the datum line. The pipe appears from 0.3 meter to 0.2 meter, and if the pressure at the longer end of the pipe is here 98,100 Newton per meter square. So, what should be the pressure on the other hand, and in this case you neglect the losses and there is no head exerted by any external machine here. So, simply we can apply this Bernoulli's equation here, the equation it is given here. So, in this case since there is no external machine is applied to deliver this liquid, so we can omit this AC term, that means here head due to the supply of energy by external machine, and H2 there is no head loss, it is there. So, H2 will be equals to 0 if we consider these two sections of this pipe, where in the one sections the cross section I think as per the it is given that cross sections, in one cross sections the diameter is 0.3 meter and other cross sections it is 0.2 meter. So, based on that if flow rate is given 0.05 meter cube per second. So, V 1 you can easily calculate and V 2 also easily calculated by flow rate divided by cross sectional area, that will be your V. So, in the V 1 it will be Q 1 by A 1 and V 2 will be equals to Q 2 by A 2 here. So, Q 1 will be equal to Q 2. So, we can say that what should be the V 1 and V 2. So, after calculation we are getting V 1 will be equals to 0.707 meter per second and V 2 will be equals to 1.592 meter per second. Then after substitution of this V 1 and V 2, then what should be the P 2 here? P 1 is given to you at these sections, the P 1 is given to you, this one is known to you. Now this one is known to you, G is known to you, rho is known to you. So Z 1 and Z 2 also known to you. Then what should be the P 2 that you have to find out. So finally P 2 is coming as 99,115 Newton per meter square. So these examples is applied just by applying the energy equations, that is Bernoulli's equations there. Other example, suppose if we use any external devices or machine, in that case what should be that head by external machine based on this Bernoulli's equation here. So in that case, if we give an example of that, a pump of 11.19 kilowatt with 80% efficiency discharging crude oil of specific gravity of 0.9 to a overhead tank as shown in figure here. If losses in the whole system is 1.5 meter of following fluid, what is the discharge head by the pump here? So in that case again, so V 1 square by 2 G plus P 1 by rho G plus Z 1 plus A C, that will be equal to V 2 square by 2 G plus P 2 by rho G plus Z 2 plus H 2. In this case V 1 is equal to 0. From this tank there will be a discharge of liquid by this pump here. So V 1 will be equals to 0 here, and V 2 that you have to find out, and Z 1 is given to you are 4 meter, whereas Z 2 it is given to you, and here 25 meter, and here P 1, what is the P 1 value is given to you, that is I think you know this P 1 value, it is given to you, and also power of this pump is given to you. I think it is 11.19 kilowatt, that means here 8.9484 kilowatt, that means 80% efficiency. So finally this will be your power of pump, and power that will be the specific gravity into Q into AC, that implies that what is that Q will be equal to this, but what is AC here? AC is the what is that head due to the supply of energy by this external machine. So if we substitute this V 1 is equal to 0 and P 1 is like this, and what is that Z 1 is 4, and here AC is unknown to you, and here again V 2 is 0, and again P 2 is also atmospheric pressure. So P 2 is 0, and then Z 2 is given to 25, and H 2 is 1.5, it is given to you. So from these equations you can have what will be the AC, that means here head loss by this external pump. Based on that power of pump, so you can calculate what should be the flow rate of this fluid. So flow rate will be is equal to 0.0571 meter cube per second. So this is your what is that discharge, and also discharge head is 17.5 meter. Now application of Bernoulli's equations, other application of Bernoulli's equations like what is that, it can be applied in practice for the following discharge measuring instruments like Venturi meter, flow nozzle, or if you split pitot tube, and problems of flow under a sluice gate which is a constriction in an open channel, that is called Euler, even radial flow, free vortex motion, etc. So all those things in you can apply the Bernoulli's equation. Based on this, total conservation of energy will be equals to same there. So we can apply in different way the application of this Bernoulli's equation. Based on that Bernoulli's equation, we can develop some flow measuring instruments, that is called Venturi meter. That Venturi meter is nothing but what is that, just narrowing the channel whenever it will be flowing through the pipe, that means narrowing that pipe and through which there will be a velocity change, and based on that velocity change there will be a pressure change by this principle of this Bernoulli's equation or energy equation. And in that case, what should be the velocity and if you know the velocity, what should be the flow rate of that. So, because the flow rate is calculated based on the velocity into cross sectional area, because the cross sectional area is known to you. So, what should be the flow rate there. And flow nozzle also there is important that in that case if we use some nozzle through which that the fluid will be flowing. So, in that nozzle there will be a higher velocity, that is z velocity. Once you know that that is z velocity, and what should be that cross sectional area of the nozzle hole size. If you know that hole size, you will be able to calculate what should be the velocity at that particular nozzles, that is z velocity. And if the conservation of the mass is there, if the fluid is flowing at a certain mass, then mass flow rate or volumetric flow rate. So, from that through a cross sections you will be able to calculate what should be the velocity there, and by this you will be able to develop a flow nozzle. And also another important, that orifice plate, another important measuring instruments by which you will be able to calculate what should be the velocity at a particular location there. And also a pitot tube, that also in the streamline what should be the what is the dynamic pressure and static pressure, you will be able to calculate by this pitot tube based on this Bernoulli's equation. And also we have already shown earlier that some sluice gate operation there, the design of that gate and how much pressure is producing there. Once the velocity through the river is known to you, then what will be the pressure will be developed based on this energy equations. Also, if you know the pressure head there in the flow, then what should be the velocity there. And through the weir also, by which you can calculate what will be the flow rate by this weir. So, that flow rate can be calculated based on this conservation of energy law. And in that case you will see that whenever fluid is flowing over that some weir, then what will be the velocity and discharge, from that you will be able to calculate based on this energy law. And also radial flow, whenever fluid is flowing through a certain angular velocity, then how this vortex will be formed, and at different locations based on this energy equations, what will be the velocity there once you know the pressure at different position. So, we can apply these energy equations in different instruments. We will be discussing later on that later on also in a separate module the function and also principle of this Venturi meter, flow nozzle, orifice plate, pitot tube based on this Bernoulli's equation. And so, in this lecture we have learned the conservation of energy, how it can be derived, and how this energy equations will give you that hydraulic grade line and the energy line, if is there any energy loss, or if is there any head is supplied by external machine, how to calculate. Even if the flow is non-uniform, then what should be that modified Bernoulli's equations there. Then there you have to consider some kinetic energy correction factor. In that case, there will be, you have to remember that kinetic energy correction factor is I think certain value for this turbulent flow and the laminar flow there. So, we have discussed here. In the next lecture, we will be discussing more about that this energy equations and energy principle there. So, thanks for all today. Thank you.